Hello, and welcome to our webinar for the December of 2019. Today I'm going to be talking a bit about some of the sensors and data logging options you have available to monitor structures, but I want to talk about a few other points before we begin. It's been a really busy year at PCTE, and we're quite proud of some of the new things that we have to present from our partners, and also a few points of news on our company. Firstly, I'd like to welcome Jun in New Zealand as our new manager there. Jun's a qualified mechanical engineer who's worked as a corrosion engineer in the past. He's also experienced with laboratory testing and has worked in research. He's joining us and has been there for a number of weeks already, and we're really looking forward to the support he can bring to our customers in New Zealand. Hello, sorry, and thank you. So this is Jun. Jun's our new New Zealand manager. Secondly, this year we've had the opportunity to present in a number of different conferences. Myself and Michael from our Queensland office were able to take a stand at Concrete 2019 from the Concrete Institute of Australia. And Stuart and Monica were able to present some of our new metal testing equipment and our concrete inspection equipment at the Australasian Corrosion Association's conference this year. We always love attending conferences. It's a great chance to meet up with our clients in different states, to show what's new and also to drill down onto a particular topic area. Finally, before we begin, I'm particularly excited to introduce a few new concrete inspection tools. These products are both from Prosec. We've recently launched Prosec's GP8800 radar in Australia. This is a really exciting product. It's a step frequency continuous wave ground penetrating radar system like the Prosec GPR Live model you may have seen before. But the big change here is that it now is more compact. The depth is not particularly affected. You go from maybe a maximum of 750 millimeters on the Prosec GPR Live GP8000 model. For the GP8800 model, you're maybe at 650 millimeters maximum depth, but your antenna size will now fit in the palm of your hand. We do have demonstration models moving around, so if you're interested to take a look, try it out in an application, see into just how tight a space you can get this system, just let your local manager know. Also new from Prosec, we have their Silverschmidt Live model. And the big change here is it's still the same Q-value Silverschmidt hardware and mechanism inside, but the data logging has been greatly improved by connecting it now into your Apple iPhones or iPads. It's also greatly improved the ability to trace and confirm and verify its function on site. There's now a range of small site anvils, which, while not a full calibration anvil, will allow a verification to be stored along with the data in the hammer, indicating that you've checked it and you're all good to go. So, now let's begin talking about the topic for today. Today's topic is going to be about our range of sensors and data loggers with a particular focus on sensors that are useful to monitor structures or monitor around structures. I don't want to just go over devices or tools like that. I'm also going to talk about some of the calculations that are needed to understand what the tools are doing and how the measurements on site get converted into engineering units that can be used back in the office. I'm also going to talk in relative detail about data logging, because the trick is not so much mounting the sensors, it's actually getting the data into a format you can use, getting access to that data in a timely manner with the constraints of access you have on site. Then finally, I've got some case studies showing examples of how you can instrument a structure to capture the critical factors around it. Sorry, 1 second. So, beginning, I just want to cover what is and is not in the scope today. Specifically, we're going to be discussing force or strain measurement sensors and displacement measurement sensors. So these are the ones that can capture what forces are doing to a structure and the motion of that structure. Now, there's a broad range of tools that these areas could encompass. On the force and strain measurement side, you have a lot of different kinds of strain gauges between pure mechanical measurements, or perhaps the most familiar resistance-based strain gauges. You also have more specialized systems like fiber optic systems. The particular scope I'm going to talk most about today is vibrating wire sensors. Our partner Geosense is an expert in their manufacture, and they have a number of advantages for long-term monitoring. So that's where I'm going to contain my effort. I'm also not going to go too deeply into sensors that might be used in geophysical or geotechnical applications. So I'm not going to be talking so much about piezometers or tools like that, but that is also a very common kind of vibrating wire sensor. So on the displacement side, while I will cover tilt meters and extensor meters and crack meters, I won't be going into a lot of detail on things like inclinometers or large-scale board extensometers, which are more to see what the soil is doing than to see what's happening on a structure. So let's begin right at the most basic tools. And these are tools where they can be used simply by visiting site and taking a measurement, or leaving some reference points on site so that an operator can return and physically measure the distance between them. For displacement, that could be something as simple as the crack monitors or telltales, the simple plastic gauges you can see on the right here, where they are glued across a join or a crack and will show motion from a 0 point in 2 dimensions. And these are a very commonly used tool, and they're very useful, but they do have some constraints. Perhaps the most critical one is that their resolution is not very high. If you can see the scale here, the smallest graduation is to 0.5 of a millimeter, and it can be quite hard to catch any motion greater than 0.5 of a millimeter with this tool. The other key thing to be aware of with any sensor or references that you place on site is you are usually most interested in relative motion. It started at this point, and 5 days later, it's moved 2 millimeters apart, or closed 2 millimeters, or it hasn't moved. Even when you have something with a 0 point, like the scale on a telltale crack meter, it doesn't mean that your initial point began at that 0. It's important after install, after the glue sets and everything's in its final state, you record the current values. So when you come back, you can reference the initial value and then the present value and get the relative motion from the starting point. Now, this is displacement. It is possible to measure strain mechanically too. You may know of a tool called a Demick gauge or a digital position strain gauge. These are, in practice, a very precise displacement measurement tool. They'll measure to fractions of a millimeter between 2 points. The reason that we can talk about these being a strain measurement too is that they capture change over a fixed length, and that's to do with the way they're installed. So the gauge itself, which you can see in the top right here, is used to record the current position of 2 monitoring studs versus each other. Now these studs have a conical point. The gauge locks into them, so it gets a very precise position. And it's the way that these are set up and the gauge is set up that let this work also as a strain gauge. Firstly, they're a fixed distance apart, placed in with a jig, which means we know the distance, which distance and displacement helps us calculate strain. The other part is that we can set up the 0 of our gauge very precisely. The calibration bar is of a metal which is less sensitive to heat, so it doesn't change length very much with temperature. and allows the gauge to be zeroed precisely before each measurement. Once again, when these are installed, they may not be exactly at 0 versus this scale, so it's important to record the initial values. But with these two factors, these digital position strain gauges can either be an extremely precise displacement gauge or can be used to calculate strain. So these are the most commonly used mechanical devices. Now, biggest limit with a mechanical device, of course, is you don't get a measurement until you send someone out to take it. And because you have an operator using a tool to measure between places, he needs to be careful and precise. And you may even find that if you send two different operators out, you can get two different values for the same measurement, which is improved a bit with a digital gauge, but particularly when you're measuring anything optical or where someone needs to read off a scale, there can be differences of interpretation. So, the next one I want to talk about, and as I said, this is a particular specialty of Geosense, is the vibrating wire strain gauges. The image I have on my left here is a fairly simple vibrating wire strain gauge. It's the same construction as this gauge here. The reason I've chosen this as my example is that this is the most basic vibrating wire measurement that we can take. Looking at the diagram, we can see that there are two anchor blocks physically aligned with a wire strung between them. That's a fixed distance apart on the one I just showed you, and in most cases that distance is 150 millimeters. This gauge is pre-tension, which means it's just fixed at a certain initial tension on the wire. And if this was to be embedded in concrete or otherwise fixed in place into a material, that tension would change as the forces around it increase or decrease pressure on it. Practically, we can record that change in tension on the wire by plucking the wire. We do this electrically with the electromagnetic coil. And then we can record the frequency of measurement. I'll talk about that a little bit more during the data logging section. But practically, the units of measurement we have for a vibrating wire strain gauge is frequency. And then by knowing the mathematical relationship and the calibration of these gauges, we take that unit of frequency and we convert across the engineering unit of strain. So, there's a couple of real advantages to vibrating wire strain gauges and a couple of disadvantages. Probably the most critical advantage is they're very simple, they're very durable, and they have a very low drift. Which means that if I take an embeddable strain gauge which has been heat treated and prepared for its life on site, and I embed it in a concrete structure, there's very little that can damage it, and the frequency is going to change mostly due to changes in the structure, rather than long-term drifts, say, of glue changes or other materials changing around it. What that means is that we can come back 1 year, 2 years, 5 years later, and we should see very little drift, very little change of the initial zero values. This makes it great for long-term structural monitoring. If we want to come back and look at the strain in a bridge 5 years later, we should still have an active working sensor in place. And it's this advantage of vibrating wire tools that lets them be used for a whole broad range of measurement tools. The piezometers pictured, very commonly used in geophysical applications. As I said, they can be installed and can monitor pore water pressures in soils for a very long time. And I've also pictured a displacement gauge, which lets us go from the very small measurements a strain gauge can take to broader measurements. Now, as I mentioned, in order to convert from frequency values in hertz across to the actual strain in microstrain, it's important we need to do a calculation. And this same calculation is going to be used for any vibrating wire sensor, but there'll be a different gauge factor, and any manufacturing batch will have a batch factor as well. So the calculation here shows a calculation for a simple strain gauge. We can see that we've been given a gauge factor of 3.7, batch factor 0.924. These are multiplied together, and then if we're looking to see the change, the initial frequency when the gauge was installed is subtracted from the current frequency and the result recorded. So this calculation can be done by the operator when given a set of measurements from site, or it's more common to have a data logger on site that will both record the frequency measurements and output a converted value in the engineering unit of microstrain, or whatever value your sensors have. So, as I said, I've begun with strain gauges. I've shown you one format of strain gauges, but there are others. There are also strain gauges that can be surface mounted, either on concrete structures or steel. Pictured here we have a strain gauge intended to be spot welded onto steel structures, and a surface mounted gauge which can be welded or bolted or bonded into concrete structures. Very flexible. In a second I'm going to talk about how to install these gauges, because these ones aren't pre-tensioned, and because they're not pre-tensioned they need to be tensioned on site. If you are specifying these into a project, the key points to capture are, what are you trying to measure? If you're putting a strain gauge in, you're going to be measuring microstrain. The practical range on these gauges can be a lot less than 1 millimeter. For example, a standard 150 millimeter strain gauge, surface mounted, has an actual displacement range of around 0.5 of a millimeter. If you've got smaller gauges or spot weld gauges, that's as short as 0.15 of a millimeter. So this is not the tool to see is a joint opening or closing, but if you were concerned with, say, is a very fine crack moving at all, it may be appropriate, or, as I mentioned, the actual strain in a structure. Now, just quickly on the installation of these gauges for surface mount gauges. This is very important. So this is a surface mount gauge, and we can see that we have two anchor blocks there. So to use it correctly, it needs to be fixed into brackets on site and then tensioned. So the pictures here show the procedure. First, the blocks are mounted in this case. In this case, they're being welded in sight, so the operator has placed a steel bar between the two blocks at 150mm spacing, and they've been welded into place. After that, the fixed end, which is the 2 Allen key end of the strain gauge, is locked into place. Finally, the operator applies a small amount of pressure with his hand, pulling the whole gauge away from that fixed block towards the floating block, and finally the single Allen key end is locked down hard. While he's doing that, he's watching a readout. This could be a readout in your data logger or a handheld readout, and he's setting an initial 0 frequency value. So for this 150mm gauge, that initial value in hertz is 1200, or in B, which is a set of units known as linear digits, which is a linear measurement of frequency. It's essentially a mathematical conversion. That would be 1380. So this is the critical step if you're using surface mount strain gauges that are not pre-tensioned. When they're tensioned in place, they'll then operate very cleanly. The other critical step with installing a surface mount gauge is that once they're locked in and you've got your initial value, they should be checked the next day to see that they are solidly locked and are still very close to that initial value. If they've moved a lot, then maybe the anchor isn't locked in place correctly, or they weren't tensioned correctly. So that's the most basic vibrating wire sensor. Let's go through a few other options you have available. A crack meter, or displacement meter, is an evolution of this design where rather than having two fixed anchor blocks that are directly connected to the structure, one end of the anchors is connected to a spring, and then that piston arrangement is then anchored to the structure. What this does is it extends the range over which the gauge can work while reducing the precision. It's no longer precise enough to measure displacements that would correspond to a strain change, but it can monitor 12 mils, 15 mils, 50 mils of displacement by the change in tension on the wire as affected by the expansion or contraction of that spring. And you've got various designs here. The most common one is the vibrating wire crack meter design, which is physically intended to be bolted across a crack or a join. So if you had an expansion joint in a structure and you wanted to see how it was moving over the long term. Did its peak displacement increase with time? This would be a very suitable tool. The designs shown here are piston arrangements where they may be fastened to push against a plate, and then if that plate moves towards them, they'll contract. There are also more specialist designs that can be embedded between joints in a slab. Now, this is where we come to one of the big disadvantages of these kind of sensors. A vibrating wire sensor is only suitable for a static measurement. It will record the strain or the displacement at a point in time. You can't collect data from them more than every couple of seconds, which is fine to see how structures change over the long term, but it's not appropriate for dynamic monitoring. If you wanted to drive a vehicle over top of a bridge with instruments and you wanted to see the effects of that vehicle live on that structure, the data could not be collected from these sensors more quickly enough. Now, moving on, we have a few other designs available. It's possible to use displacement gauges with a cable connection to catch displacement over a longer distance, similar to a tape extensometer. It's also possible with this particular jig to use a analog sensor like a 4 to 20 milliamp transducer. I'll talk about this under data logging when I talk about other kinds of sensors you may want to connect into your data loggers, because vibrating wire is a little more complicated to data log than simple analog sensors. And a final point on displacement on structures is that you can come up with arrangements, either manual or with displacement sensors, that are going to capture 3D motion. This is two examples. The example on the left is intended to capture motion similar to a Demick gauge, but in three dimensions. So handle displacement gauge can pick the change in one anchor from the other. The other instance shows a similar setup with two anchors, but in this case, it's intended to capture displacement using a vibrating wire displacement gauge. So that could go straight into a data logger and could record that value. One of the big reasons you would go from manual measurements to an electronic measurement like a vibrating wire gauge or a displacement gauge is simply you can't get back to the same place. If it's underground or you need to bring in access equipment, even if you don't leave a data logger on site, leaving sensors on site can allow someone to access a junction box where access is convenient. It doesn't require equipment or special paperwork. Another special application, this is a vibrating wire strain gauge installed on stranded anchors. So like you may find in a post-tension tendon or like you may find in suspension bridges. They're intended to be put in place with grout, but they allow the active strain to be monitored inside those strands. So it's a very special application of the same principles. Now, moving on to a second kind of sensor. We talked about strain. It's possible to measure force directly as well, rather than the effect of that force. Most commonly done using load cells, which can, depending upon their arrangement, measure either a tensile or compressive force. I've put here three different kinds of sensor. The top right corner is a sensor which is just a conventional strain gauge load cell. The lower one is a vibrating wire gauge load cell. And the final one is a pressure load cell. So they all measure the same factors and they've each got an advantage and a disadvantage. The strain gauge based load cell could be used for dynamic monitoring. So if you wanted to see exactly what happens as you apply force with a jack into a post-tension tendon, a vibrating wire strain gauge may be a very appropriate choice. They're very responsive, they're fairly compact, and they can sit into that system as they measure. Now, the vibrating wire load cell may be more appropriate to monitor the tension on that tendon over the long time. So if you wanted to leave a sensor in place for many years, it's a better choice with all the advantages of a vibrating wire sensor. And the pressure sensors are a simple, low-cost tool. And it is possible to take them from a readout like shown here to electronic monitoring by installing a pressure sensor of some form along with them. Okay, so before I go on to the final kinds of sensors I'm going to talk about in this first stage of the seminar, I just want to talk a bit about tilt and measuring tilt, because it's easy to say we put a tilt sensor on a structure and we see how it moves. But it depends upon what type of structure you have, what is actually going to affect that sensor, and the right choice of sensor to measure deflection with tilt. So just a couple of important terms. So if we talk about tilt on a structure, we're talking about the tilt of the whole structure. So the rotation about a point to a different angle of the whole structure. So if it's a building, that'll be the whole building tilting left or tilting up or tilting down. So we can see this is useful information, but it wouldn't capture, for example, if there was differential settlement. Say that the middle of the building had sunk into the ground, but the 2 points had not moved at the far corners. If we had tilt sensors only on those corners, they wouldn't pick up that differential settlement. So that's where the concept of angular distortion comes in, which does pick up differential settlement between 2 points. So again, if there was a structure that was constructed of masonry and had suffered subsidence on its left-hand side, and there was a tilt meter on its right-hand side, a point, just a single box measuring tilt, the left-hand side may subside into the ground, but because that tilt meter is still on a fully supported part of the structure, and there's some ability for the bricks to move relative to each other, the tilt meter by itself would not pick up any measurement. But if we had a tilt beam connected from the left to the right-hand side of that structure, essentially, which was then measuring angular distortion rather than tilt between left and right-hand points, that subsidence would be captured by that device. And you can extend this further by using arrays of tilt sensors that can pick up the deflection over the entire structure. Finally, relative rotation is a very similar parameter to angular distortion, but it's more about the rotation of a straight line between two reference points. This is particularly important if you are using arrays of tilt meters. So, just to illustrate what I mean by this, we can see here there's enough tilt on the building of the left-hand side that the tilt over of the entire structure can be seen by eye. And because it's rigid, that line is still straight and it's deviated from 90 degrees vertical across. On the right-hand example, it's quite hard to spot by eye that the right-hand side is lower than the left-hand side, but by looking at the angular distortion between the two, it can see that the left has dropped relative to the right. And it's that relative measurement that is important, because typically if you are using a form of tilt meter, it's not going to be an absolute measurement. So let me just go through what you can use to measure tilt. The most basic tool is a tilt meter. These are most commonly a MEMS sensor, which is a form of electrical measurement. Practically, they are going to output in the engineering units, once they've been converted, an angle of tilt. And there's special options available for submersion in water or measurement. But the key thing of these is that a point measurement. So if I take a tilt meter and I put it on a steel beam, and that steel beam moves, because of the stiffness of that steel, it's entirely appropriate to just have a tilt meter attached and to capture that directly. Similarly with a bulk concrete structure, the whole structure should move responding to heave or settlement, which is one of the most common tools you would catch with a tilt meter. The other thing with these is when I get to data logging, I'll talk more, but these can output in a format that's friendly for an analog data logger, or they can output directly the measurements to a digital data logger. Now, tilt beams are more appropriate to capture displacement on a structure where you may see relative change in it, like a masonry structure or brick structure. There's two ways this can happen. If you have a tilt beam that stretches between 2 points, any differential settlement between those points won't be captured, but the angular distortion between the 2 points will be captured. Going beyond that, by using arrays of tilt beams, the relative displacement along the entire structure can be captured. So in that situation where we do have a subsidence in the middle of a structure and the points on the left and right hand side weren't able to be seen, an array of tilt beams would capture that differential change. Now, the final thing is these do not capture absolute measurements, they capture relative measurements, usually within the structure itself. One more. No, this is an in-place inclinometer. It's another kind of tilt sensor more commonly installed in the ground around a structure to capture, again, relative displacement using tilt. So if we do want to capture an absolute heave or settlement, we need to use a different principle. So this is a vibrating wire settlement monitor. And it's quite clever. There are two components. There is a reservoir, and that reservoir is able to provide a fixed point of measurement. So if we take this distant to the structure on a piece of ground that will not move, and we place it there, then we then run a tube to carry the water pressure from that higher position along to a vibrating wire pressure sensor attached to the structure or buried beneath the structure, and then there is heave or settlement. That pressure sensor moves up or down. The height of water above it will change, and the pressure will change. So you have a direct measurement of heave or settlement. This illustration shows how that would work. So this is one way to monitor absolute heave or settlement, whereas tilt beams are monitoring a structure's motion relevant to itself. So that's just a quick overview of some of the more commonly used sensors. In many cases, you can measure the same properties in other ways. So if we want to measure tilt, we could use a MEMS tilt meter, or we could use electrolytic tilt meters, or we could use a survey system. Similar, if we want to measure strain, there's other forms of strain or displacement sensors that are available. So now that I'm going to talk a bit about data logging, I'm going to talk a bit about each kind of sensor, their pros and their cons, and what kind of data log is needed. So, to begin, let's talk about analog sensors. So I've used this as a fairly broad term, but these are typically the easiest kind of sensor to connect to a general data logger or to something like an industrial automation system or a hobby microcontroller like an Arduino or a tool like that. They will all have a frequency response that they are sensitive to, but it's going to be quite a lot faster than a vibrating wire gauge, so they're going to be more appropriate for dynamic monitoring, situations where you want to catch dynamic changes in load or strain. Some of the most common is a 4 to 20 milliamp current loop. This is very common with industrial automation. It allows for a long cable run and simple interfacing. Millivolts or voltage values are less flexible, but they're the easiest to connect to a data logger. Nearly any kind of analog input to a computer is going to be able to accept some range of voltage values. So by scaling that voltage into it, it's a very straightforward sensor to integrate. And finally, and a very common kind of sensor, is a resistive strain gauge. Now, this is a passive sensor. In order to measure from a resistive strain gauge, they need to be connected to a fairly precise measurement circuit, like a Wheatstone bridge, and they might need some form of amplifier in your data logger. So that's a very common tool, but it's not quite as easy to log measurements from a strain gauge sensor as it is from sensors that are a voltage or milliamp output. We've discussed vibrating wire sensors. As we've said, they're very good for long-term installs. The cable runs can actually be extremely long because the frequency signal is more or less insensitive to most forms of noise and the cable is shielded. You can do hundreds of meters of distance between vibrating wire sensors to the data logger. We can't monitor them dynamically, and they need a special circuit. So this means that if you're selecting a data logger from a range, it's not possible to assume that the data logger will be able to record values from a vibrating wire sensor. You need to pick something appropriate. So from our range, that would be any data logger which is intended to go with geophysical or structural sensors. but it's a question that needs to be asked. And if your data logger cannot accept vibrating wire sensors internally, it'll need an interface of some sort to convert the vibrating wire frequency values across to a voltage or milliamp value that a data logger could understand. Finally, the digital sensors is a bit of a misnomer. The sensors are always analog. Sensors are always going to output something that needs to be measured by an analog to digital conversion circuit. But when you have a digital sensor, or maybe even something which would be called a smart sensor, what that really means is that the analog values are collected, measured, and recorded from an analog voltage value or whatever it outputs across to a digital point of data, and that can then be transmitted along some form of data line, or if the case of a smart sensor, it would be sent along the internet. So essentially there's additional circuitry with a digital sensor. The most common one, from what I've been talking about, is tilt meters, which are, because often you want to run dozens or several tilt meters together, situated in a line, they're very commonly supplied with an RS485 digital connection. That's a bus connection, which essentially means you can plug them in a line together, and then the data logger will send a request. Sensor number 7 down the line, send your current results back. Okay, good. Sensor number 8, send your results back along the line. This has big advantages because you're not running 17 cables from your data logger, you're running 1. And it also reduces the requirement to measure very fine changes on the sensor at a point distance to the data logger over the cable. Instead, the cable just needs to send a fairly easy to transmit digital signal along. Now, it's not the case that you need to use a data logger on site to collect data. As I mentioned, where you are mainly using sensors to improve access, but you still want to revisit and record data manually, a readout would be appropriate. There's various forms of readout. Some of them are fairly simple devices that just measure one kind of sensor and report its current values. Others have a range of sensors they can connect to or include some data logging, which lets you save records of the measurements. So in the examples I've got here, this is an MP12 readout. It's a very simple readout, but it can record data from a variety of analog sensors, from vibrating wire sensors. It can also record temperature data from common thermocouple or thermistor sensors. So it's a very flexible tool. This example is a vibrating wire sensor, which is specifically intended to read values on a vibrating wire sensor. It makes it very easy for the technician to operate on site because he plugs it into the same colored plugs, turns it on, takes the values away. And this is a more clever example, which is intended to connect to a box multiplexer on site. So 15, 16 sensors could be connected into that box. This data logger connects to that box and lets the operator read off the values from all those sensors in turn. Again, all ways to improve quality of life recording data from these sensors on site. Perhaps the most familiar tool to people might be a conventional data logger setup. And by that I mean a data logger that has 2 or 5 or 16 input channels, and it needs to be set up for the particular job on site, usually by a skilled programmer or person very familiar with the data logger interface. Accessories need to be supplied for the number of sensors that are going to connect to it, so it's common that you'd use multiplex units to collect many dozens of sensors to a single data logger. You might need an accessory for a vibrating wire sensor. You might need modem accessories to allow remote access to the data. Essentially, a conventional data logger is the most flexible tool, but it requires someone skilled with that particular data logger setup and to have a broad skill set for things like telecommunications, internet protocols, and to essentially be able to provide a finished solution, which is the data logger, any interface for the owners of that data, any internet websites needed to connect with that data. But this is what's used at the endpoint of many more complex monitoring jobs, and they definitely make sense beyond fairly simple parameters. The other option for data loggers, and these can do a lot of jobs, is a simplified data logger. So the two examples I have here is a geologger links and a geologger 485 SDI data logger. These are intended to be simple enough that someone who understands the sensors can set them up and give it parameters for a particular sensor type. So the geologger links is a vibrating wire data logger, and geologger SDI is it's a tilt meter data logger for what we've been discussing, but it's actually a data logger that can connect to any 485 bus sensor string. So that could also be used for things like inclinometers. So let me show you how you'd set up something like this. This is the software program for the Linkstyle logger for a vibrating wire sensor. And what we can see here is all of the specifications a user can enter. So he's able to record information about the name of the sensor, its serial number, what kind it is. This is more information for record keeping. He also gives it the operation parameters for that sensor, which means which frequencies it needs to measure through to catch the operating frequency range of the vibrating wire sensor. It's because most vibrating wire sensors also include a temperature sensor. The user has specified the kind of temperature sensor. He's also given it a 0 reading, which is essentially that's our initial value. So that's where our relative strain or relative displacement would deviate from. And he's chosen a VW conversion, and he's put in his polynomial factors. What that is that's the calculation. That's where the operator will enter in his gauge factor and his batch factors. This same data logger can act as a live readout. So this is showing it monitoring a single piezometer sensor. And it's just doing that live on a computer. And here's an example of how he sets up the data logging. So he's able to choose up to 4 data logging steps. So he could tell it to record values every hour or every minute or every day from the sensors, choose the channels, and set that data logger going. When you're setting this kind of tool up, you balance between the period of time you want the sensor to operate independently. These are battery powered, so if you want it to run for a long time, it's appropriate to choose a short time for the data logging interval. To choose quite a distance between data. You might want to measure once a day, then the battery life on site will be very long. If you measured once every minute, it would have quite a short battery life on site. Finally, there's an output sample here, which shows the measurements, essentially recording engineering units along with a backup recording of the raw units from a sensor, which is very important. You always want to capture the exact measurement of the sensor in case something was wrong with the batch factors or conversion factors entered. It allows the operator to go back and redo those calculations, provided he's got the raw measurement data. So that's sensors and that's data logging. So when you face a project where you do want to use tools like this on site, it's important to establish what sensors you want to place on site, how you're going to get data from them, and how much setup is going to be needed. Do you need a solution including programming and conventional data loggers, or can you install half a dozen sensors and a simple strain gauge data logger yourself, simplifying the job and also simplifying the maintenance? It's also possible with any data logger to connect that out to the internet. The geologger links data loggers have a ability to connect to remote FTP servers or a couple of third-party monitoring dashboards. So there's always a way to get that data off-site without revisiting it if need be. So these examples I'm going to talk about now, they're specifically about some ways the sensors can be placed around a structure to capture particularly important properties. Then I'll finish on a quick case study, which is going to look at an example of doing that in London, where they used the heave and settlement the head pressure monitors I mentioned to catch change along that distance. So looking at our examples, the first one is going to be, this example is more about capturing what happens around a tunnel structure. This is a typical example of all of the instruments that might be installed around a freshly bored tunnel to capture long term. So there's relative displacement from the surrounding earth using multi-point extensometers. Strain gauges and pressure cells monitor the force coming from the outside onto the tunnel structure and what strain that is caused by. The tape extensometer measurement, so this would be a manual measurement someone would conduct by visiting and taking these measurements, catches displacement relative of the tunnel. Now, extending beyond that, it's possible to, over the length of that tunnel, catch relative displacement using tilt beams, absolute displacement using something like the liquid level system I spoke about, and also displacement between segments using crack meters. Now, looking at structural monitoring, again, tilt meters on a stiff structure can capture relative displacement and tilt. Liquid level systems would be appropriate tools to monitor the absolute position of that structure versus its surroundings. And this is also a case where the axis is correct to use something like a total station to monitor the structure as well. Now, the foundations, depending upon what's nearby, additional extensometer tools and inclination tools can capture what's happening in the structure. Now, an interesting example here, this is a very common job done using vibrating wire strain gauges. It's to instrument a pile before load testing of that pile. What they do here is they will cast a pile with many dozen strain gauge sensors cast into that pile, and they'll be at different heights. And what they can do there is they can work out, is that a friction pile or is it an end-bearing pile, and see the effects of their load test. So in this example, they've placed a load cell above the pile and have applied a particular load to that pile through the load cell, capturing the absolute load applied. And then they can capture the change in strain. So in this case, because the load distribution essentially bottoms out at the bottom of the pile, most of the force of that pile is held by friction. This is a interesting and clever application of measuring indirectly where the load is carried by that pile. So the final example I have here is a case study, just looking at the use, some of the data you can get from the heave and settlement monitors. So in this case, they were tunnelling underneath central London, and they had more than 1,500 hydrostatic level cells installed. And the attempt here was to catch any settlement and to use a compensation grouting procedure, pumping back up the ground underneath the buildings so no building underwent greater settlement than was desirable. So the way that installation might go is to catch the settlement. They would have various instruments installed on the structures, and then they would grout from underneath that structure to restore its position. So in this, we now have the output from several settlement monitors and the effect of each round of grouting activity. So as the structures settle and reach a threshold below, in this case, 4 millimeters, the grouting restores the height, in each case towards the end of the project. So this has been a very quick overview of some of the sensors that we can supply, some of the ways they can be used, and some of the nuances in data logging for vibrating wire and other sensor types. Does anyone have any questions? I'll be watching the live chat, and I'd be very happy to go through anything more that I can help with. Thank you. As I said, this is our last webinar for the year, and we're looking forward to coming back in 2020 for more training content and more live events. Now, if I haven't covered something particular to your particular interest, there are other ways PCTE can help out. For example, we do have a range of sensors and data loggers suitable for corrosion monitoring of structures, which are a bit outside today's scope. So if you want to learn more about that, you can talk with your local manager who can prepare a custom presentation for you, or even a custom web chat or live stream specific to your business. I've done that several times for areas like talking about basic crack measurement and other tools for my customers. So if I can help, or anyone in the company can help, please do get back in touch. Now, I'm not seeing anything coming through on the live chat just yet, but I'll wait a few more minutes before closing out the webinar. And thank you very much everyone who's attended. Okay, that's when nothing has come through. Thank you very much for your time and your attention.